Okay, so today we're going to look at the intersection of two planes. First thing to recognize is what are the possibilities, and just kind of visualizing them. If two planes do intersect, they're going to be intersecting at a line. So all those points along the intersection will create a straight line. Obviously, again, remembering that the planes are going out infinitely in all four directions. The line will be infinitely long as well. And then the other possibility is the two lines are parallel, so they're side by side, one over top of the other, something like that. So as we're going through these, we're going to be considering those two possibilities. So first example, find and it's a line of intersection, remembering that these are the direction vectors in scalar form. We need to determine, first of all, whether we have parallel planes or not. And so that'll be the first thing to consider, simply because it's the much quicker, much easier thing to consider. We don't want to waste our time looking for the line of intersection if in fact there isn't one. So quick review, if we have two vectors to determine whether they're parallel, and these ones turns out are, let's guess that this thing looks something like 6, 2. We want to remember that to have two vectors be parallel, then we can write something that looks like this. We can write them as scalar multiples, one of the other. Sorry, square bracket here. So basically, because I know they're parallel, that means there's some value k, or I guess we've tended to use t and s, where 3 times this value will give me 6, and 1 times this value will give me 2. Obviously, in this case, that value is 2. For any other parallel line, though, this same sort of thing will occur. So let's assume that I have this going out much further. Whatever this is, as long as it's parallel, then we can write there will be a t value for which this works. So again, I don't know exactly where this goes out, or how far this goes out. It goes out to an xy value out there somewhere. But the fact that they're parallel means this does exist. So the same will occur now. If two planes are parallel, then their direction vectors will be scalar multiples of each other. And so that means that I'm looking to determine whether there's a value of t in the case of the example above. Again, just chose t, such that this direction vector is equal to t times the other direction vector. And so the math of it is pretty simple, really. I'm just looking to figure out what would the t value be that gets me, that when multiplied by -3 gets me 6. Well, obviously it's -2. And then I'm asking myself, basically, is there the same value in all three cases? So -2 is equal to t times this 1. If it's the same value, then I'm in good shape. Again, same value. So since they're all the same, therefore the planes are parallel. If there isn't a consistent value in all these three spots, then the two planes, are not parallel. The two vectors, the direction vectors are not parallel, which means the two planes are not parallel, which means I then have to do a little bit more work. So I've changed the question a little bit. Changed this, it was a 2. Yeah, it was a 2. I changed it to -8, or sorry, it was a -2. I changed it to 8 here, 7 here, just so I know that these are not going to be parallel. And I could test that, of course, but I know that, just based on what I saw last time, these won't be parallel. So the question is, what are we going to do? And we have now two equations with 3 unknown values. you know from before, back again, going back to grade 9 initially, if I have two equations with two unknown values, I can use elimination or I can use substitution, and I can solve for the x value, the y value, the point specifically where they intersect. So at first glance, when I look at this, I see there are three unknown values, there are two equations. My first instinct might be to say that I can't actually solve this. Of course, that's not true, but what we're solving for now is a line. So in my final answer, there will still be a variable. There's not one point. There's not a 3, 7 or a 2, negative 21 that I can find. But there's a series of points represented by some sort of a line. And so what we're going to do is basically simplify this to the point where, maybe I'll even jump ahead and peek at the answer. I end up with symmetric or really parametric equations to represent my line. So how do we get there? Go back and we'll go through it. So the first thing we're going to do is basically choose a value or a variable to eliminate. Out of force of habit, I tend to eliminate y and then z and rewrite the other two terms in terms of x, the other two values in terms of x. Certainly you can do any one of them, but that's kind of the standard we've adopted. So equation 1 is this one. Equation 2, do this a little bit neater, is this one. And essentially, in order to get the elimination here, I need to line up my y values so that the coefficient is the same. And so what we had originally was that we're going to multiply equation 2 by the value 8. And so you can see that negative 3 times 8 is negative 24, and so on. Again, don't have to probably go through this in too much depth. I'm then going to add the two expressions, the two equations, and I get negative 18. I get the 0y, and of course that's what I'm looking for. I want to make sure I don't have y's in my final expression, final equation. Wow. And once I have this, I can rewrite in terms of z. So z is the same as negative 18x minus 187 over 25. Continuing on, I will do the same thing for z. So the exact same series of steps. Obviously what I'm multiplying by in this case changes. So I've got 4 times equation 1. And I've got 7 times equation 2. And you can see that what's happening this time is my z values are lining up so that the coefficient is the same, or at least the opposite of each other. Again, in this case I'm going to be adding. And so add these together, get 3x, add these together, negative 25y, add these together, and then isolate y again. So I've written z and y in terms of x. Now, to rewrite this as a line, we've already sort of previewed that we're going to be writing the parametric equations. And so we want x in terms of t, y in terms of t, and z in terms of t. Well, by letting x be t, we can simply substitute t for x in the other two expressions. And I have this, and this as my values for x, y, and z. And those are the parametric equations. Once I know those, of course, I should be able to write the other two forms. The vector equation, x, y, and z are made up of however many of each of the other values. So rewriting the vector equation for y so that we have it in sort of more standard form. This part of it here, negative 123 over 25, is the y value of the point. This is the z value of the point in the vector equation, and this is the y value of the direction vector, the z value of the direction vector. X itself, I didn't write the same way, but x is the same as, I guess I should have rewritten these in different order, but 1t plus 0. So 0 is the coordinate of the point, 1 is the x value of the direction vector. Now, the symmetric equations here, typically what we'll do is isolate t. That's, of course, what this symmetric means. I've got each of my expressions in terms of t, and then I make them equal to each other. What you'll find here, or what you might recognize here, is I don't have exactly what I want in my symmetric equations. I want this in the form x plus or minus some number divided by its direction vector. Obviously, in this case, divided by 1. I could say that it's x plus 0 or x minus 0. So this one is actually in the proper form. But having the 25 here means it isn't really the symmetric equation that I want it to be. I would like to see y plus or minus some number divided by some value, knowing that the number on top then is the y value of my point, or at least allows me to establish the y value of my point, and the denominator will be the direction vector, or the y value of the direction vector. So really what I've got here, if I write these perfectly, I end up with y plus 123 over 25 on top, divided by 3/25 in the denominator. Same sort of thing here. I end up with z, it's plus 187/25 on top, divided by negative 18/25 in the denominator. The only reason that occurred was because I made up these questions from the start, and we ended up with fractions going all the way back up to these values. Some nicer numbers, and I wouldn't have a 25 here, and then everything would simplify nicely. Your symmetric equations would look perfect from the start. So this is fine as an answer. We typically would probably just stick with our parametric equations and say we're done. Rewriting them this way will get us to the answer, but recognizing the true symmetric equations would not have the 25s in here. They're just a little bit messy to write. So I'll jot them in here at the end. I'm going to pause the video just to write it. Okay, so down here at the bottom again, this is really sort of how we like to see our symmetric equations, because now my point is very easily recognized. It's this minus this value, minus this value, minus this value, or the point 0, negative 123/25, negative 187/25. My direction vector appears in the denominator. But again, I can only read that off when I have just z, just y, and just x isolated in my symmetric equation.